Okay, I just wanted to make a quick video about how to use stat key for a hypothesis test to get a p-value using a randomization distribution. I thought that was there in Melissa's videos, but it's not. Well, I guess maybe not all. We don't need this fifth one, the slope and correlation. We're not there yet, but the other four could potentially show up. So the single proportion is what we'll start with since that shows up in the lab. So beyond the numbers 3.31 in the workbook, number 1 and number 2, that's what those are. Those are hypothesis tests for a single proportion. So we'll start with that. I threw a few things together in this PowerPoint. Essentially, I'm going to use the single proportion case for just kind of the mechanics of it. That's why I've got all three of the possible inequalities in here. There's really not a ton of variation between the first two, to be perfectly honest. I mean, it's either you're in the left tail or you're in the right tail. What you would do with a two-sided alternative is a little bit different, though. But still not too bad. So if we're just going to run through these in the order they show up, so let's see, if I go back here to stat key, then where we want to be is a test for a single proportion. So what you have to do, what you have to adjust in here, you have to adjust the value in the null hypothesis in most cases, unless the default happens to match up correctly. If your null hypothesis was p equals 0.5, then you don't have to change anything, but we're going to, because the first example here is p equals 0.3 for the null hypothesis. So, okay, we're going to have to change that. So if I change that 0.5 to a 0.3, and then in order to get your sample proportion in there, you have to go to edit data, and then you just have to put it in essentially as a fraction. So the sample size, I mean, that's going to be your denominator. The count is the numerator. It's how many times in the sample that some event of interest occurs. So what we've got here for this first example is 53 out of 200. So that's what I'm going to need to put in here. So 53 out of 200. Okay, and oh, I forgot. When you put these in, and I'm glad I made this mistake. Granted, I don't have a lot of time to have a bunch of takes like I did in the other video, so I kind of have to do this all in one take, and I did kind of screw this up. But I'm glad I did, because it's really easy to screw this up. I did this first. I changed the value for the null hypothesis, and then I went and put in the sample proportion. If you do that, stat key for some reason resets the value in the null hypothesis. So you're actually supposed to put the sample proportion in first and then change this. Otherwise, you have to change this twice, which is what I'm stuck with. So if I click on this, the 0.3 is actually in there. But then now if I click on OK, it's going to display correctly. All right, so now I need to generate my samples. So at least 5,000, right? So I'll just put in 5,000. If I go back to the PowerPoint for a second, I've got a less than here. So where that comes into play with finding the p-value is, that means it should be a less than in the picture as well. So you're going to want left tail. And then you want to cut that tail off at p hat, because generally the p-value is how often you would get a sample proportion that's at least as extreme as the one that you got in your actual sample. So what we're going to want is, if I go back here for a second, 0.265 and below, right? So if I go back here, then I just have to change this cutoff to 0.265, right? That's just 53 divided by 200. And there we go. The p-value is 0.165. All right, so that's the first one. The second one, it was a greater than instead of a less than, and like I said, there's not much of a difference, but it's worth going through one. So some weird numbers here for the sample proportion, not that that actually matters, right? You still do the same procedures. If I go up to edit data, now it's 214 out of 419. I think I remembered that correctly. Okay, yeah, I did. And then the null should be p equals 0.5, which stat key just kind of reset for me. All right, so now if I generate a whole bunch of samples, so again, I'll do 5,000, and now it's a greater than in the alternative hypothesis, right? Here's the greater than right here. So in order to account for that, that means the p-value should be a right tail, right? That's the greater than direction. So if I go back here, then I want to select right tail, and then I need to cut this off at 214 divided by 419, which is 0.511, at least that's what it is to 3 places. You can certainly carry it out farther than that, but stat key can only handle 3 places, so that's why I rounded off there. So if I go back here, if I cut this off at 0.511, there's the p-value, 0.318. Okay, so the one-sided alternatives are pretty similar to each other, right? It's either left tail or right tail based on if you have a less than or a greater than, respectively. The two-sided alternative is slightly different. So that's this third one, where I have null of p equals 0.75 versus an alternative that p is not equal to 0.75. And then I've got my p hat down here. So, okay, let's see, 237 out of 300. So that's our sample proportion. So 237, 300. Okay, and the null is p equals 0.75. Okay, and then generate a bunch of samples. Alright, and the sample proportion works out to be 0.79, right? It's here in the PowerPoint, there's the 0.79. So I need to use that as a tail cutoff still, but I need to use two tail here, right? It's a two-sided alternative. You got the not equal to in the alternative hypothesis. So two tail, and then I just need to cut off the right tail at 0.79. And I'm just using the right tail because 0.79 is bigger than 0.75. Right? If our sample proportion was something less than 0.75, the value of the null hypothesis, then I'd be specifying the bound in the left tail. And then if I say OK, there we go. I guess the one thing to be careful of with the two-sided alternative is that you need both pieces for the p-value. So what I mean by that is, yes, you need this part, the 0.059 up here for this right tail that's bounded by 0.79, but in order to account for both directions, which is what you have to do when you have a not equal to in the alternative hypothesis, you also need this left tail down here. So the p-value really is 0.059 times 2, so 0.118. So effectively what's going on here is when you select the two-tail option up here and then specify the bound on one of the tails, then what stat key will do is it'll give you the proportion in that tail, and then it'll manufacture a tail on the other side with the same proportion. So effectively you're just doubling that one tail. Another way to do it, and this isn't more correct or less correct than doubling one tail, would be to have two separate tails where the bounds are the same distance away from the hypothesized value. So in this case 0.75. If you were going to do it like that, you could. So this is an alternate way of doing the exact same thing. Instead of two tail, if I had left tail and right tail, and then I cut this off at 0.71, because 0.71 is the same distance away from 0.75 as 0.79 would be, right? Between 0.75 and 0.79 you have a 0.04. Between 0.75 and 0.71 you have a 0.04. Right, it's just here it's 0.75 plus 0.04 to get up here, and then 0.75 minus 0.04 will get you down there. And yeah, these two tails aren't the same size, right? This is a little bit smaller than this one over here on the left. You can do it this way if you want to. It's more work to do it this way, I think. So just taking the two-tail option, specifying one bound based on what your p hat is, and then just effectively doubling that tail, I think is the easiest way of handling it. Okay, the other options, if I back out of here and go to the stat key main page, would be a single mean, difference in means, difference in proportions. I know the next example I've got in the PowerPoint is for a single mean, so I'm just going to go right to it. So the single mean, I've got this example here. So average FICO credit score last April was 695. We have a random sample of 20 current FICO scores. And then does the sample provide evidence that the average FICO credit score is no longer 695? So if there's anything to pull out of that last sentence, the most important, and there certainly is, but the most important thing to pull out of that last sentence is that you have a two-sided alternative. Because it says no longer 695. There's no specified direction, not that is it now higher than 695, it's not is it now lower than 695, it's just is it different, is it something else. So it's got to be a two-sided alternative, so this would be a scenario where you would have a not equal to in the alternative hypothesis. So even though they're not visible here, really what you would have for the hypotheses, your null hypothesis here is mu equals 695, and your alternative hypothesis is mu is not equal to 695. And again, it's a two-sided alternative because there's no direction specified over here. Okay, so if I go back to stat key, we're going to have to dump out this preloaded data for body temperature. And I'm not going to use a header row. I've copied that table into Notepad because the formatting here matches stat key, so I can just copy it, paste it, and then I don't have to do any extra formatting. And then just say OK. And then we have to change the null to mu equals 695. OK. And then generate a few thousand randomization samples. Then to tail, right? It's supposed to be a two-sided alternative. It's not here on the PowerPoint what the sample mean is for these 20 scores, but it's in stat key. If you look over here on the right where it says original sample, then where it says n equals 20 and then mean equals 712.25, that's the sample mean, the 712.25. So that's what I'm going to use as the cutoff for the right tail. And again, I'm using the right tail cutoff because 712.25 is bigger than 695. So I'm just going to change this to 712.25. And there we go. So it looks like what we're getting for a p-value is 0.38 because you need the 0.19 for this tail plus the 0.19 for that tail. And there we go. Presumably there you would not be rejecting the null, right? 0.38 is a lot bigger than 0.05, which would be the conventional significance level, but the only other ones that really come up with any sort of frequency are 0.01 and 0.10, and certainly 0.38 is a lot bigger than those too. All right, other options would be the difference of means and the difference of proportions. So let me go back for a second. These are a lot like what you would do for a single mean and a single proportion. It's just that you have to input more stuff, basically. Oh, and that you have a fixed null hypothesis, which is either that the two means are equal or the two proportions are equal. I'll show you what I mean by that. Stat key just has a default setup for the null hypotheses for these two options right here. So for a difference of means, I believe that's the next one I've got in here. Yes, it is. Because the wolves, those are weights, that's quantitative, this is means. All right, so we've got the weights of two samples of wolves for different regions of Mexico. And let's say that what we wanted to do is see if there's evidence of a difference in mean weight. So the mean weight of adult gray wolves in Chihuahua versus the mean weight of adult gray wolves in Durango. All right, so this is a difference of means. And if we go here to stat key, then if we put our sample data in, let's see, I did kind of forget to do this correctly, but I can fix this quickly, I hope. All right, so let's see, the Chihuahua ones in my Notepad file are these, so I'll just copy these over. All right, so the one thing that you have to do is when you put the data in for a difference of means, you have to specify which sample each number goes in. So I'm using a C for Chihuahua. That's what that C is for. I figured that would be the most descriptive thing that I could use that was also really short. And then, let's see, underneath that I have the Durango numbers. So, let me just grab a hold of these. And then I'm going to use D for Durango to specify that that's the sample that these go with. These are from the Durango sample. So, let's see, it'll take a few more seconds for me to get all these in. And I don't really have a lot, oops. I really don't have a lot extra to say to fill up the space right now, so it's just about done. Okay, now it's all in there. So if I generate, oh, and again, notice the null hypothesis is not something that you can adjust. It's just this mean is equal to this other mean. So the null hypothesis is just going to be the two means are the same. And we said that what we were going to look for is just to see if there's a difference in average weight of the adult gray wolves in those two areas of Mexico. So we'll generate our several thousand randomization samples. And we'll say two tail. And the difference in sample means is 8.97. Right, it's up here in the original sample part up toward the upper right. And then, I guess upper right in relation to where the picture is. And then, again, I'm going to be cutting off the right tail because 8.97 is bigger than 0. Right? If the null hypothesis is mu1 equals mu2, then that distribution is going to be centered at 0. Right? Because if mu1 equals mu2, then mu1 minus mu2 equals 0. Right? So 8.97 was the difference in sample means. So if I use that for the cutoff, it looks like what we're getting. So 0.0084 times 2, so that's what, 0.0168 for the p-value. It feels like I've just been doubling the right tail every time. I guess if I had these in the opposite order, so if I had the Durango ones first and then the Chihuahua ones, then we would have gotten negative 8.97 for the difference in sample means, and then I would have been doubling the left tail, right? Because negative 8.97 is less than 0. So that's just sort of happenstance that's been doubling the right tail every time. If you're getting a negative for something like this, I mean, that certainly is a value that's less than 0, and then you'd be specifying a left tail cutoff. Okay, the other option is a difference of proportions, which is actually what you have to do for the project. So, all right, difference in proportions, and okay. So this is another one where at least there's a little bit more wording this time, because some of the homework problems look like this too, right? Where there's a bunch of wording. So what we're supposed to be looking for here is to see if women make bail at a higher rate than men. So this is going to be a one-sided alternative, right? Because yes, we're looking for a difference, but we're looking for a difference in a specific direction, right? A higher rate for women. That's a specific direction, so it should be a one-sided alternative. So it's going to be set up like this. Okay, so what we have for women is 15 making bail out of a random sample of 20. For men, we have 9 making bail out of a random sample of 20. Okay, that's enough to do this. So for a difference in proportions, I need to edit the data. I guess I'll do it as women then men. You can do it as men then women, but then you kind of have to flip everything. You'd have to kind of reverse the order of the alternative hypothesis as well. That's fine. I mean, that's a completely valid maneuver. But here it's slightly extra work. It's better just to go women than men here. So 15 out of 20 for women, and then 9 out of 20 for men. Okay. And we'll generate a few samples. And notice this doesn't fill in too much, right? Like there's nothing in between these two bars, and then these two bars, and then these two bars. Right? There are these big gaps in the graph. That's because there are no possible values in between. So, like, there isn't really a way to get, for example, a 0.15 here. It's just not a thing that you can have. So, if it looks a little bit weird, that's why. It suggests that there aren't too many possible values here for the difference in sample proportions. So, our difference in sample proportions from the two samples, as opposed to any of the randomization samples, is 0.3, because 15 out of 20 is 0.75, and then 9 out of 20 is 0.45. So the difference between 0.75 and 0.45 is going to be 0.3. Okay, so then we just have to specify, in this case, right tail, right? So we're doing, if I go back for a second, this is our alternative. So I guess another way of looking at this would be the alternative could be phrased as P sub W minus P sub M is greater than 0. Right, if you look at the randomization distribution, that's centered at 0. So it should just be a right tail, and that's what we're going to end up with. It's going to be a right tail bounded by 0.3. Right, that's where this is going to come in handy. That's going to be our tail cutoff, so I'm just going to say right tail. And this, I didn't anticipate that this would happen, but I'm glad it did. It looks like you have the answer already, that it's 0.025, and it's not. The default for stat key is to cut this off so that there's a 0.025 in the tail. If I click on this and then retype 0.3, I'm actually going to get a bigger p-value. The reason for that is if you look at this right here, so just this bar right here, part of it's red and then the bottom part is black. That's because this isn't including that black part as part of the p-value. So if I click on this, put in a 0.3, see? Bigger p-value. And that's what you have to do here, because just by definition, the p-value here is supposed to be the chance of getting a 0.3 or anything larger. So you need all of this 0.3 bar and then all this stuff. So now this is set up correctly. Before, where this was partially black and partially red, it wasn't, and you're going to get a p-value. It's too small. So it looks like what we're supposed to get for the p-value here is 0.055, and that's right. Oh, and I didn't point it out earlier, but again, with the null, it's fixed. So for a difference of proportions, it's fixed to be just that P1 is equal to P2, or effectively P1 minus P2 equals 0, and that's why this distribution is centered at 0, right? The randomization distribution is going to be centered there. Okay, that, I think, covers the different mechanical possibilities that you might run into. Right? There were a couple of two-sided alternatives in there. Had at least one less than, although I think it was only just one, and then a couple of greater thans. So hopefully that'll clear things up a little bit if you're stuck on what to do with stat key as far as how to get the p-value. If not, I guess email me, but hopefully that'll kind of take care of just about everything.